Hello, welcome to the session about using image comparison algorithms to detect malicious zero-day applications and domains. Let me introduce our presenters. My name is Pavel Kaczma, and I work as Threat Labs manager. Along with me is Surabhi Kapoor, our data scientist. The agenda is I will speak about why we use image comparison, how we use it, then Surabhi explains science behind it, and then there will be space for questions. Any successful detection algorithms consist of multiple layers. In this talk, we show how machine learning can help us in detecting situations when an attacker mimics an icon of a trusted service or application to trick users into taking an action they wouldn't normally take. Phishing attacks are the practice of sending fraudulent communications that appear to come from a reputable resource. The goal of the attacker is to make the user believe that the fake site or application is legitimate. On the left side is an example of a legitimate site. On the right side is the phishing site mimicking the original one. Both sites are almost identical, but image comparison of whole pages is a resource consuming task. So instead of that, we focus on the dominant visual elements, icons. Example of the extracted icon is below the screenshot of each web page. Icons are important for the initial resource recognition, and also icon comparison is cheap in terms of computing power. On this slide, we have an example of phishing attack against a popular game, Among Us. On the left side is the legitimate application. On the right side is an application using visually similar icon, just upside down. Our goal is to identify sites and applications with visually same or very similar icons. We perform proof of concept to validate that convolutional neural networks can be used to detect situations where an attacker is trying to mimic icon of a popular site or application. This is an ongoing work. First, we identify the most common targets, for example, Facebook or Outlook login page, TikTok or Minecraft application. We use statistics over our data about traffic and applications used by our customers. Then we collect original and slightly modified icons. We are looking for visually similar icons, not binary identical. Then we built a convolutional neural network able to detect similarities between two inputs. Evaluation is done by comparing the icon of an analyzed site or application against our dataset. If it matched, we raise a flag. We don't block a site or application only using visual similarity because of high risk of false positive alert. We block a site or application only if we have multiple indicators of malicious behavior. And now I pass the word to Survey.
As Pavel mentioned, that at Windera we continuously try to improve our phishing detection activities, and over years we have developed multiple flags to which collectively tells us about the maliciousness of an app. Lately, we have come across situations where hackers try to imitate the icons of the app to trick the users. So, we perform the proof of concept to validate whether convolutional neural networks can be used to develop this new flag, which will detect whether the icon of an app is being mimicked or not. For this purpose, we collected images of icons from Google Play Store and only considered top 5% of most popular apps with more than 50 million installs on Google Play. We further split this huge data set into training and validation data sets, each containing 594 unique app labels. Moving on to the algorithm we used, we used convolutional neural networks which can take an input image, assign importance to its various features like colors, shapes, and objects, and differentiate the images on the basis of those features. On the slide, you can see a basic architecture of a convolutional neural network, which is a series of multiple layers, each of which tries to learn and refine more on the basis of these features and learn as much information as possible about the image. The next two slides will tell us about how our model performed on the dataset. We tried two different convolutional neural network algorithms named MobileNet and Inception V3. The line charts on the slides tell us about the validation, accuracy, and loss of the models as we trained them over 50 rounds of training. The x-axis tells is representing each round of training, and you can see that we train the models for 50 rounds. These rounds can be named as epochs, and the y-axis summarizes the accuracy and loss of the models respectively. As you can see, it is very evident from the line charts that the accuracy of the models is increasing at every step of training and the loss is decreasing. This is the expected behavior of the convolutional neural networks. We can say that the models performed better at each step of epoch as the accuracy is increasing and the loss is decreasing. You can also look at the table at the bottom of the slide, which summarizes the validation accuracy and the validation loss of both the algorithms at the final 50th epoch. And we can see that the accuracy and is of Inception V3 model is more than that of MobileNet V2, and the loss of Inception V3 model is less than that of MobileNet V2, which means that Inception V3 performed better than that of MobileNet V2, and hence our final selected algorithm. Moving on to the next slide, which tells us about how our model predicted the images on the validation dataset that we had. The line chart on the left summarizes the stats about how many images were correctly classified, incorrectly classified, and not classified by our model at various probability thresholds. The x axis of this chart represents the probability thresholds considered between zero point 0.3 and 1, and the y axis represents the proportion of the images. Now, analyzing this line chart, we can see that our model could correctly classify most of its images at all the probability thresholds, where and also from the yellow line you can see that we have more non-classified images at the higher probability thresholds than not correctly classified images. Moving on to the images on the right, you can see that our model could correctly predict the rotated image of Twitter with 99.9% confidence, an image of Dell with a deleted patch with 99.9% of confidence again. And the third image is of a gaming app, which we labeled as multicolor. Our model could predict its image with an additional sticker of 2019 with 81.7% of confidence. So overall, we can see that convolutional neural networks is a good choice for this for predicting whether hackers are trying to mimic icons of apps or not. And the model we trained was of accuracy 93.24%, and it could predict most of our images correctly. But at the same time, a model is still susceptible to some false positives as it predicted some of its images incorrectly. So, our at the later stage, we now want to concentrate on various strategies about how we can improve our neural network. Because at this stage of POC, we focus more on validating whether we can use convolutional neural networks or not. And so we kept everything very simple to understand and easy. But at later stage, when we actually start our project, we will be focusing on making this model more and more accurate with very less number of false positives. Moving on to the next slide and passing it on to Powell again.
All the results we talked about today is not representing the final model, but results of the proof of concept show potential to detect zero-day attacks and opened space for a novel detection method. Thank you for listening.